Hello everyone, Namaste. I am Ramnath who would like to share with you some information on the VLSI topic, why EM in soft design an issue to be solved. This is part 3 and final part. Please feel free to provide your comments or any suggestions. Thank you. In the earlier part of the series, we have understood how electromigration will cause hillocks or void formations. In this specific slide, we will try to understand how the metal atom moving will cause a open circuit. So there are two methods by which this can happen. So in the first method, metal conductor resistance increase leading to joule heating, which is same as I square R. So the temperature will increase because of high current, and because of that the high temperature, again the more electromigration will happen. Because of that, again the resistance increase because of lack of atoms. Okay, and that will again be in a loop, and it will cause destruction of the metallic interconnect. In the another method, metal track width eventually reduces to a narrow enough cross section of the metal, which will lead to high current density, which means again which will lead to higher electromigration, which means again the width will further becomes narrower. So again current density will increase. So these form in a loop, and which will result in a runaway condition. However, this electromigration can also be come to our rescue in protecting important electronic systems. So we have also observed in our home that the fuse exists in the home before it is supplied to any electronic or electrical equipment. So if you observe how the fuse work, it can work either in terms of electromigration concept, or it can be affected by thermal rupture. So we will see how the temperature gradients in the metal wires will affect. So that can be temperature gradients can happen either through joule heating inside the wire, which is caused by high currents. A perfect example is a fuse. So here the fuse is shown here. So I square R will happen because of high current, and hence the temperature is increasing because of heat dissipation, which will lead to higher thermal migration. And in the another method, external heating of the wire, such as caused by high power dissipating devices nearby. In one example, in the earlier Power 4 server chip, if you observe, these are the same blocks. So here the temperature profile of the same block have been shown. You will observe that one part of the temperature shown in red color is at 82 degrees centigrade, and some portions which are in blue color are at 66 degrees. So it is close to around 20 degrees temperature difference or gradient exists within the same chip, which will increase the speed of the atomic movement. Yeah. So in another approach, but temperature gradients can also increase when there is not enough cooling to the wire. Usually in the lower geometry nodes, now through silicon vias are employed. They are connected to the heat sink. Thus, the heat is dissipated, and the wires are kept at lower temperature. And another way by which the temperature gradients will increase is, say in the ICs, when some special considerations are not taken, whenever there are any sharp wire bends, current crowding will occur. Because of that, the high current, again you can consider that joule heating, and then it will lead to higher temperature and thermal migration will occur. IC failures are usually repairable IC or non-repairable condition. Okay, so the repairable condition is characterized by MTBF, which means mean time between failures. You can usually see them between clock domain crossings or reset domain crossings. However, non-repairable failures are characterized by mean time to failure. We will discuss about mean time to failure in this slide and further, because those are the ones which are related to EM failures. So EM probable failure is broadly modeled through Black's equation, and if you see the Black's equation, which is a MTTF equal to A j to the power of minus n a to the power of EA by KT. A is a constant, J current density, n is a model parameter which is usually 2, okay, but it can range from 1 to 2. And EA is the activation energy, K is the Boltzmann constant, T is the absolute temperature in Kelvin. So mean time to failure is a maintenance metric which measures the average amount of time a non-repairable asset operates before it fails. Okay, so learning more about Black's equation, we will find that Black's equation does not represent the EM behavior fully. That means physically it does not represent, but it gives a largely broader picture. Hence, even in lower geometry nodes, still Black's equation is used. Okay, so it predicts the lifespan of interconnects in ICs under stress conditions. We also need to know that usually the lifespan of interconnects is much larger than consumer ICs lifespan. Hence, not usually earlier there were not so many failures, even though the Black's equation interconnect failures have not been studied grossly. So MTTF of a system is given as the average time between the failures of a system, and if you see, there are so many devices or elements or interconnects in the system, and if you take all of them reciprocals, here N1 is the MTTF of a system or a component 1, and N2 is the MTTF of component 2, like that, then MTTF of the system depends upon 1 by N1 plus 1 by N2 plus 1 by N3, like that. So the weakest link dominates. Hence, we need to identify the weakest interconnect which is causing the lowest MTTF, and then we need to improve the situation. That is why if you observe the electromigration depending items, then you will understand that it depends upon frequency, wire size, wire material, temperature, operating condition, voltage and large driver. So you will observe that here the constant A depends upon the wire size, wire material, temperature and the operating conditions also. Okay, so we need to know that all these things indirectly depend upon A, and the voltage will directly influence the current density. Okay, and here the temperature directly influence the uh, mean time to failure. If you observe the wire material, it should be better it is gold or silver, but because of the cost reasons, copper or aluminum is used. However, gold is also used in specific last mile connections. So if you see, copper is way better, close to 5 times better than aluminum in terms of electromigration for the same reliability need.
Yeah, Black's equation is commonly used to predict the lifespan of interconnects in ICs. Okay, under stress. So this model is this model's results can be extrapolated to the device's expected lifespan under real conditions. So to figure out those real conditions in the silicon estimating stage is somewhat difficult. So what is done is, like, the device is taken through high temperature, elevated temperature, and higher voltage, stress voltage, I mean, and then it will be taken through the as per the mission profile of the product. So this is done to ensure the qualification standards. So automotive electronics council have some standards. In that, Q100 is one of the standards to take the automotive products through it. So in for rugged vehicles and satellite applications, the standards will be different, and for commercial applications the standard will be different, and stress, hence the stress conditions will also be different. So for each use case of the product, in the mission profile, it will specify a summary of operating conditions. That means, like, at -40, how many number of hours and what is the voltage at which it operates. Similarly, at 70 degrees, uh, how many number of hours it operates and what is the voltage. Like that, different specifications are mentioned in the mission profile, and this will be used to calculate the to arrive at the accelerating factor. So that accelerating factor is used, calculated based on the temperature at which the HTOL testing is performed at elevated temperature and at accelerated voltage. Usually the accelerated voltage is performed usually at 1.4 times the normal maximum voltage. Okay, so based on this, the number of hours to be performed in HTOL is determined. There is a, and this HTOL results should be predicted as per the failure mechanisms. Here, since we are considering the electromigration is the main failure mechanism, so we have to appropriately put the uh, uh, accelerate failing mechanism factors in analyzing the device failures, and thus we will get the associated mean time to failure. So how this will affect is, like, the failure rate. Say this failure rate can happen through multiple failure mechanisms. That is what the HTOL mechanism will try to figure out. Okay, and one of these mechanisms is EM. So assume that we are figuring out the early mortality failures. So this is very similar to the infant mortality in the children. So children usually have high death rate in less than 11 days. That is why naming ceremony is also conducted after 11 days. Okay, so once that 11 days period is crossed, the death rate will not be so high. Okay, so similarly, even for the once the failure mechanism here, the early HTOL condition, all the other quality tests have been performed, the failure rate will be very constant and it will mainly depend on the random failures. So after a certain number of years, again due to aging, the failure rate will increase. So this is the usual bathtub curve uh, of the failure rate. Okay, this is similar to early life failure rate. Okay, here the failure rate is in the y-axis and time is in the x-axis. For different applications like commercial applications, military applications, and automotive applications, and satellite telecommunication applications, the in number of years will differ. For automotive, usually it is 15 years. EM violations were first analyzed on power and ground lines. Later, signal EM also became prominent as geometries reduced and the frequency of operation increased. Okay, so DC electromigration really affects power and ground delivery networks, and AC signal going through any intra or interconnect signals of the design should be considered for root mean square or peak signal or average EM analysis. Okay, and the high operating cover frequency naturally affects the larger leads to larger RMS current, and hence it will affect the EM violations more. Okay, so electromigration, as we know, it depends on multiple factors, and frequency, wire size, wire material, and all, and wire size, wire material, all these things, and temperature, all these things are specified, coded in the QRC tech file, which is nothing but the interconnect data file format, where the RC information of the fab will be coded uh, based on what is the width of the metal layer, and what is the spacing between the two metals, and how much will be the uh, current density associated with it, all these things. Okay, so based on those specific conditions, operating frequency, these RMS current density, and peak current density, average current density will differ. All those values will be represented in the QRC tech file, okay, or fab specific technology file. Okay, this is for the EM, and in the left file, that is broadly or grossly coded based on that. Yeah. So from here, the design, when it is taken through and analyzed at different operating conditions, either RMS or peak or average, the EM violations, whatever pops up for the specific scenario or mode under consideration, should be cleared by appropriately changing the wire size, because that is the only um, uh, attribute or control generally available with the soft designer. Okay, so if there is any change in the wire material and all, that should be done at the fab level. Okay, most of the times that will not be uh, have the flexibility for the sound designer. Temperature is also one more condition that the architecturally, if we can handle, then also the EM violations will reduce. Sometimes if you reduce the large driver feeding the interconnect, then also EM violations will reduce. Yeah, that's all we have on the EM. And there is one more small thing I want to mention, that how an irrigation dam is built. If you consider that one, you will also understand how the interconnects operating condition time the RMS, peak and average, all these things should be considered. You will also understand, because in the when you are considering the irrigation dam, you will understand that the water flow through the dam during the normal period or the maximum flow period, like that you need to consider different factors in designing the dam. Okay, yeah, I hope you have got some good information on this, and please let me know if you have more questions. Yeah, these are the references I have gone through for presenting the topic on EM. Thank you for watching. Bye.